Two galaxies are locked in a slow-motion collision 60 million light-years away. This cosmic wreckage, known as the Antennae Galaxies, holds secrets that are rewriting the rules of the universe. By the end of this journey, you will know 28 strange phenomena that challenge everything we thought we knew about how galaxies live and die. We will uncover hidden black holes feasting on stars and investigate the puzzling case of missing dark matter. What does a place of such immense violence and creation tell you about the story of our own cosmos? The violence of this cosmic collision is forging new suns at a staggering pace. This is the first of our strange phenomena, an unprecedented starburst. Within the tangled hearts of the Antennae Galaxies, stars are being born at a rate that dwarfs anything in our own galactic neighborhood. Imagine the most fertile, explosive nursery for stars you can conceive, and you are still only scratching the surface. This starburst is one of the most intense ever witnessed in our local universe. The mechanism is both simple and devastatingly effective. As the two galaxies grind together, their immense gravitational forces act like cosmic hands, violently squeezing the colossal clouds of gas and dust that drift between the stars. This compression is so extreme, so forceful, that it triggers a chain reaction of collapse. Pockets of gas become so dense and hot that nuclear fusion ignites and a new star flares to life. This is not happening in a few isolated locations. It is a galaxy-wide frenzy, resulting in the birth of millions of new stars all at once. Now, contrast this with the serene pace of star formation in our own Milky Way. Our galaxy is a stable, mature spiral, a place of relative cosmic calm. Here, perhaps one or two new stars are born each year. In the chaotic wreckage of the antennae, that number is in the hundreds, maybe even thousands. Think of the difference between a quiet, gently flowing river and a raging, catastrophic flood. This starburst is the flood, a deluge of stellar creation on a scale that is almost impossible to fully grasp. But such furious birth cannot occur without consequence. What happens to all these new stars crammed into such a volatile region? The very forces that gave them life are also a recipe for an even stranger and more violent future. This furious birth gives rise to the second strange phenomenon, superstar clusters. These are not your average collections of stars. Imagine packing the mass of 1 million suns into a region of space so tight that it would fit easily within the distance from our sun to its nearest stellar neighbors. The result is a dazzling, almost impossibly dense city of stars, shining with the light of countless newborns. These superstar clusters are the titans of the stellar world, and they are forming by the dozens within the antennae's chaos. They represent a mode of star formation so extreme that it simply does not occur in placid galaxies like our own. The violent merger provides the perfect recipe for their creation. When those colossal clouds of gas and dust are compressed by the galactic collision, they do not just fragment into individual stars. Instead, they collapse into these monstrous, singular entities, birthing hundreds of thousands of stars all at once, all bound together by their own immense gravity. This makes them a unique and precious laboratory. Normally, astronomers study stars that are scattered across vast distances and born at different times. But here, in a superstar cluster, they can observe 1 million stars of the same age, all composed from the same primordial material, all evolving together. It is like having a single, massive experiment running in deep space, allowing us to watch stellar evolution play out on a grand, accelerated scale. The significance of these objects stretches far beyond the immediate violence of the collision. Astronomers strongly suspect that these superstar clusters are the infant versions of the most ancient structures in our own galaxy, the glorious globular clusters that orbit the Milky Way's halo. Those ancient, dense balls of stars have long been a mystery. How did they form so long ago with such incredible density? the Antennae Galaxies provide a live-action replay, showing us that the answer lies in the intense pressures of galactic mergers in the early universe. Within these brilliant new clusters, we are witnessing the birth of cosmic structures that will likely persist for billions of years, long after the galactic wreckage around them has settled. Those spectacular arcs that give the antennae their name are a cosmic illusion of the grandest kind. From our distant vantage point, they look like solid, graceful arms reaching out into the void. But they are not solid structures at all. These are the tidal tails, and they are the third strange phenomenon, a ghostly signature of the collision's immense violence. They were forged in the first close passes of the two galaxies, when their gravitational fields engaged in a ferocious tug of war. Just as the Moon's gravity pulls on Earth's oceans to create tides, the gravity of each galaxy pulled on the stars, gas, and dust of the other. But this was not a gentle pull. It was a catastrophic wrenching, so powerful that it flung entire solar systems and colossal clouds of raw material out into intergalactic space. The result is these vast, streaming rivers of cosmic debris, each one a collection of countless stars and the raw stuff of creation cast out from their galactic homes. This process creates a living fossil record. By studying the precise composition and motion of the stars within these tails, astronomers can rewind the clock. They can trace the trajectories of these exiled suns back to their points of origin, piecing together the exact sequence of the galactic collision. It is like finding scattered pieces of a shattered vase, and by analyzing the break lines, deducing the precise angle and force of the impact that broke it. The tails are not static sculptures, they are dynamic timelines written in starlight. They tell us which parts of the galaxies were stripped away first, and how the gravitational forces shifted and intensified as the cores of the two galaxies spiraled closer together. Yet for all the history they preserve, these tidal tails are also sites of profound mystery. What becomes of the stars and planets cast adrift in these lonely streams? They are now unmoored from their parent galaxies, destined to drift in the cold darkness between galaxies, perhaps for all eternity. This grand expulsion forces us to confront a startling question about the nature of such cosmic violence. If so much material was thrown out, what other strange objects might have been left behind in the chaotic center of the merger? Deep within the brilliant chaos of new stars and superstar clusters, a darker population lies hidden. This is the fourth strange phenomenon, a secret census of stellar corpses revealed not by light but by its absence. The Antennae Galaxies are teeming with black holes and neutron stars, the dense remnants of massive stars that lived fast and died violent deaths. We cannot see them directly, for they are the ultimate cosmic vaults, trapping even light itself. Yet they betray their presence in the most dramatic way possible by feasting. When one of these invisible objects orbits a normal star, its immense gravity can rip material away from its stellar companion. This stolen gas does not fall in silently. It spirals inward at tremendous speed, forming a searingly hot disk of material around the black hole or neutron star. As this matter is compressed and heated to millions of degrees, it glows not with visible light but with incredibly energetic X-rays. From our perspective, these objects flare into existence as ultra-luminous X-ray sources, or ULCs. They are cosmic lighthouses broadcasting in a language of pure energy, signaling the presence of a hidden monster enjoying a violent meal. The sheer number of these X-ray sources in the antennae is what makes it so strange. In a calm galaxy like our own, such bright, feeding black holes are relatively rare events. But here, in the aftermath of the collision, they are everywhere. This abundance is a direct result of the starburst we witnessed earlier. That frenzy of star creation produced a disproportionate number of massive stars. These giants burn through their nuclear fuel in only a few million years before exploding as supernova, leaving behind either a neutron star, an object so dense that a teaspoon of its material would weigh 1 billion tons, or a black hole, a region of space where gravity is so strong that nothing can escape. The chaotic environment of the merger then pairs these corpses with new companion stars, creating the perfect conditions for these X-ray feasts. This tells a profound story about the life cycle of stars in extreme environments. The antennae are showing us that cosmic violence begets more violence, not just in the birth of stars, but in their spectacular deaths and the hungry afterlives of their remains. Each brilliant X-ray flash is a clue helping astronomers piece together the ultimate fate of the most massive stars in the universe. If this many stellar corpses are being found, what even larger, more terrifying creatures might be lurking in the darkness? The brilliant X-ray flashes from hidden stellar corpses point to a deeper, more fundamental mystery hiding within the antennae's chaos. Astronomers studying the motion of stars and gas throughout the colliding system have uncovered a profound puzzle, a fifth strange phenomenon that strikes at the very heart of our understanding of the cosmos. There appears to be a significant amount of dark matter missing. This invisible substance, which does not emit or absorb light, is the hidden scaffolding of the universe. We know it exists because its immense gravitational pull dictates how galaxies spin and how they move within clusters. In a normal, undisturbed galaxy, dark matter forms a vast spherical halo that envelops the visible stars and gas, acting as a cosmic anchor. Yet in the antennae, something is wrong. The observed gravitational forces simply do not match what our models predict if a full halo of dark matter were present. The merger seems to have stripped a great deal of it away. How do you lose something you cannot even see? The answer lies in the unique and violent physics of a galactic collision. Think of the merger not as two solid objects smashing together, but as two vast swarms of stars and dark matter particles passing through one another. The visible stars, while numerous, are so spread out that they rarely collide. They simply slide past each other, guided and flung by gravity. The dark matter particles, which barely interact with each other or with normal matter, do the same thing. They pass right through the chaos. However, the immense clouds of gas and dust are a different story. They are tangible, they collide, they compress, and they feel friction. This is the key. During the first violent passes of the galaxies, the gravitational pull from the dense cores and the sprawling dark matter halos wrenched on this gas. But the dark matter itself, being so ghostly, was not effectively pulled along with it. A significant portion of the normal, visible gas was dragged out of the galaxy's grasp to form the spectacular tidal tails, while a corresponding amount of the invisible dark matter was left behind, failing to follow its visible counterpart. This creates a bizarre and counterintuitive outcome, a system where the visible matter and the dark matter have been partially separated by the very forces that brought them together. This phenomenon challenges our most fundamental models of how dark matter behaves. If dark matter can be so easily stripped away and left behind in the emptiness of intergalactic space, then our simulations of galaxy formation may need a serious revision. The Antennae Galaxies are acting as a colossal natural laboratory, showing us that in the most extreme conditions, dark matter might not be the unwavering anchor we always believed it to be. What other cosmic rules might be bent or broken in this arena of creation and destruction? This separation of dark and normal matter leads us to the very substance being flung away, the raw material of creation itself. The sixth strange phenomenon is a fountain of molecular gas on a truly galactic scale. Deep within the antennae, astronomers have mapped vast rivers and colossal clouds of cold molecular gas, the primary ingredient for building new stars. This is not the hot, diffuse gas that glows with energy, but a frigid, dense fog where molecules like hydrogen can form and cling together, the perfect nursery for future suns. Yet in this chaotic environment, these nurseries are behaving in a way that defies simple expectation. They are not just sitting still, passively collapsing into stars. Instead, the entire system is in violent motion. Enormous clouds of this star-forming gas are being hurled outward from the galactic center in great arcs and streams, while other streams are falling back in. It is a cosmic fountain, a cycle of creation and expulsion happening simultaneously. The forces behind this are immense. The combined energy from countless supernova explosions and the fierce stellar winds from all those newborn massive stars acts like a colossal pump. This energy injects itself into the surrounding gas, heating some of it, pushing other parts, and launching these vast structures on trajectories that carry them far from their point of origin. It is a self-regulating and incredibly messy process. The same merger that compresses gas to make stars also unleashes the fury that then flings the unused gas away. This creates an interstellar environment of unbelievable complexity, a churning ocean of material where the conditions for star formation change from one moment to the next. A cloud might begin to collapse only to be ripped apart by a nearby supernova shockwave or sent spiraling outward on a fountain it cannot escape. This dynamic chaos is a nightmare for astrophysicists trying to model how galaxies evolve. Simple equations about gas pressure and gravity are not enough. You must account for these huge, energetic flows, these galactic-scale fountains that redistribute the very fuel for future generations of stars. The antennae show us that a galaxy is not a static container. It is a breathing, erupting entity. This fountain ensures that the starburst will not consume all its fuel in one frantic burst. It spreads the wealth or perhaps the poverty across a wider area, potentially seeding star formation in the tidal tails or simply storing gas for a quieter future. How does this relentless churning affect the ultimate fate of the merger, and what strange new structures could form from this recycled material? This overlapping of galactic cores presents a unique observational puzzle. We are witnessing two separate disks of stars, gas and dust, each billions of years old, now superimposed from our distant vantage point. It is like trying to study two distinct forests by looking at a single, blended photograph where all the trees appear to be in the same place. Astronomers are faced with the immense challenge of disentangling which star belongs to which original galaxy, which supernova erupted in which disk, and how the light from one core is being filtered and altered by the dust of the other. This cosmic overlap creates a phenomenon of light echoes and mirages. When a brilliant supernova explodes in the background galaxy, its light does not travel directly to our telescopes. Instead, it first passes through the veils of dust in the foreground galaxy. Different wavelengths of light are absorbed or scattered in complex ways, creating a delayed and distorted signal. We might see the visible light from the explosion dimmed and reddened, while the infrared radiation, which can punch through dust more easily, arrives with a different intensity and timing. This is not a simple blur, it is a dynamic, multi-layered filter that changes our perception of every event happening within the collision. The overlapping geometry also creates the potential for a subtle form of gravitational lensing. The combined mass of the two galactic cores warps the fabric of space-time around them. Light from stars and background objects is bent along this curvature, acting like a natural, albeit messy, telescope. It can subtly magnify distant objects behind the antennae or create multiple, distorted images of the same event. While not as pronounced as the lensing from a single, massive galaxy cluster, this effect adds another layer of complexity to an already chaotic scene. Every measurement, every calculation of distance and brightness must account for this invisible lens, so the very act of observing this collision is itself a collision of perspectives, a cosmic hall of mirrors where light itself becomes a trickster. How can we ever hope to understand the true nature of these galaxies when our very view of them is so fundamentally warped and intertwined? Beyond the distortions of visible light, the Antennae Galaxies broadcast their chaos on an entirely different frequency. Strange, colossal lobes of intense radio waves balloon out from the galactic cores, a phenomenon that reveals an invisible landscape of high-energy violence. These are not the gentle radio whispers of a quiet galaxy. They are a roaring testament to the sheer power unleashed by the merger. The source of this radio symphony is twofold. First, consider the aftermath of all those supernova explosions. Each detonation creates a rapidly expanding shell of debris, a supernova remnant. Within this chaotic shell, electrons are whipped to nearly the speed of light, spiraling around magnetic field lines. This frantic motion generates a specific type of radio emission, a clear signal of stellar death on a massive scale. Second, and even more powerfully, are the supermassive black holes thought to be at the galaxy's hearts. As these monsters accrete matter, they can launch jets of charged particles traveling at relativistic speeds. These jets plow into the surrounding intergalactic medium, inflating giant, bubble-like structures that glow fiercely in radio waves. What makes the antennae's radio lobes so anomalous is their sheer size and complex morphology. They are not neat, symmetrical bubbles, but distorted, tangled structures that mirror the visible chaos of the collision. This tells us that the magnetic fields threading through the system are themselves being twisted and amplified by the merger's violence. The entire region is becoming a powerful particle accelerator, generating a fog of cosmic rays, which are atomic fragments traveling at incredible speeds. These rays interact with the magnetic fields to produce the very radio glow we detect. The unusual intensity of these lobes suggests that the antennae are far more efficient at this process than most other interacting galaxies. The constant compression of gas, the shock waves from countless supernova, and the feeding of black holes are all combining to create a perfect storm for generating and confining these high-energy particles. This makes the system a natural laboratory for studying how magnetic fields evolve and grow stronger during galactic collisions, a process that may be crucial for understanding how the most massive structures in the universe come to be. If the visible light shows us the birth of stars, these radio lobes show us the explosive aftermath and the hidden, energetic forces that will ultimately shape the merger's final form. This cosmic dust, a fine and powdery grit forged in the hearts of dead stars, shrouds the antennae in a perpetual twilight. But this veil hides a secret glow, a ninth strange phenomenon that reveals the true scale of the starburst. To our eyes, much of this galactic collision would appear dim and obscured, yet when viewed through an infrared telescope, the Antennae Galaxies become one of the brightest objects in the entire sky. The reason for this brilliant transformation is the dust itself. All those newborn, massive stars are flooding their surroundings with intense ultraviolet and visible light. This radiation slams into the countless dust grains that fill the space between the stars. The dust absorbs this energy, heating up until it is warm, almost toasty by cosmic standards. And just like a hot stove element that begins to glow with a dull red light you can feel more than see, these trillions upon trillions of heated dust grains re-radiate that captured energy, but they do so at a much longer wavelength in the infrared part of the spectrum. It is a colossal energy conversion happening across the entire galaxy. This is why observatories like the Spitzer Space Telescope and now the James Webb Space Telescope have been so vital to understanding the antennae. Their infrared eyes are perfectly tuned to see this specific glow. They can peer straight through the opaque clouds of dust that block our visible light view, allowing us to witness the stellar nurseries hidden within. It is like using a thermal camera to see the heat signature of a fire raging behind a dense wall of smoke. Without this infrared vision, we would be missing the full picture, seeing only the light that escapes the edges of the chaos. The sheer intensity of this infrared glow tells astronomers just how much star formation is really going on, hidden from our normal sight. It confirms that the starburst is not just a surface-level event, but a deep, pervasive fire that has ignited the very heart of these galaxies. So the dust that seems to hide the action is actually broadcasting its own detailed report, a thermal map of creation itself. But if we can now see through the smokescreen, what other invisible forces are at work, shaping the destiny of all this newly formed starlight? The same violent chaos that births stars also flings them away. Among the brilliant superstar clusters, some of the most massive suns are not staying put. They are becoming stellar fugitives, runaway stars catapulted through space at speeds that defy imagination. These are not gentle wanderers, they are cosmic cannonballs ejected from their birthplaces by gravitational forces of unbelievable power. The primary mechanism is a gravitational slingshot within a dense cluster. Picture a tight-knit group of young, massive stars all pulling on each other with their immense gravity. When two stars swing close together in a complex dance, their interaction can act like a slingshot, transferring so much energy to one of them that it is flung clear out of the cluster and often right out of the galaxy itself. We are talking about speeds that can exceed 1,000,000 miles per hour, velocities so great that the star is destined for the emptiness of intergalactic space, never to return. Another, even more violent ejection method comes from a stellar companion's death. Many massive stars are born in binary pairs. When one of them exhausts its fuel and explodes as a supernova, the explosion can be asymmetrical, kicking the remnant neutron star or black hole like a rocket. But if the dying star is in a binary system, this sudden loss of mass and the explosive kick can violently disrupt the pair's gravitational bond, sending the surviving star careening off on a new high-speed trajectory. The evidence for these runaway stars is written across the antennae in faint, glowing trails. As these massive fugitives tear through the surrounding hydrogen gas, their intense ultraviolet radiation acts like a cosmic blowtorch, ionizing the gas and causing it to glow. They leave behind slender, finger-like structures pointing directly back to the violent clusters they fled. Each trail is a ghostly arrow, a time-stamped record of a dramatic escape that occurred mere thousands of years ago. These stellar runaways are more than just a fascinating spectacle. They are crucial evidence of the extreme dynamical processes reshaping the galaxies. They prove that the violence here is not just about creation and destruction, but also about expulsion, scattering the products of the starburst far and wide. What becomes of these lone stars and any planets they might have carried with them, cast adrift in the eternal night between galaxies? These runaway stars are not the only volatile giants in this cosmic storm. Among the countless new suns, a few stand out as true titans, unstable behemoths known as luminous blue variables. These are not ordinary stars, they are cosmic time bombs ticking away in the heart of the Antennae stellar nurseries. Imagine a star so colossal that it pushes against the very limits of what is physically possible. A star so luminous that its own light threatens to tear it apart. Luminous blue variables are among the most massive and brightest stars known, but their brilliance comes at a cost. They are in a state of perpetual, violent instability. They do not burn steadily like our sun. Instead, they undergo gigantic eruptions, casting off entire shells of their own mass in cataclysmic outbursts. In a single event, a luminous blue variable can eject more material than the mass of our entire sun, creating a vast, expanding nebula around itself. The Antennae Galaxies, with their frenzied production of supermassive stars, provide the perfect breeding ground for these rare and short-lived monsters. Their presence is a direct consequence of the intense starburst, creating conditions where stars can form with such immense bulk that they are doomed from birth to a turbulent and brief existence. Watching a luminous blue variable is like watching a star in its final, desperate acts. They lose so much mass through these eruptions that they completely alter their own life cycle, shedding their outer layers until they expose their searing hot cores. This extreme weight loss program is crucial, as it may determine whether the star ends its life in a relatively quiet collapse or in one of the universe's most spectacular explosions, a hypernova or a long-duration gamma-ray burst. The intense ultraviolet radiation and powerful stellar winds from these variables are also sculpting their surroundings on a grand scale. They blow enormous bubbles in the interstellar gas, clearing out regions of space and influencing the formation of future stars. Each eruption seeds the surrounding cosmos with heavy elements forged in its core, enriching the galactic environment for the next generation. In the Antennae, we are not just seeing stars being born, we are witnessing the most dramatic and unstable phase of a massive star's life, a fleeting, brilliant struggle that holds the key to understanding the fate of the very largest stars in the universe. If these giants are so volatile, what other extreme events might their deaths trigger in this already chaotic environment? This relentless production of unstable stellar giants turns the Antennae into a supernova factory. The sheer number of massive stars born during the collision's starburst phase guarantees a correspondingly high death toll, making this region one of the most prolific producers of supernova in the nearby universe. These are not rare, isolated events here. They are a near-constant drumbeat of stellar catastrophe, each explosion a brilliant flash signaling the end of a star and the violent beginning of something new. The life cycle of a massive star is brutally short. While a star like our Sun will burn steadily for billions of years, the true behemoths formed in the Antennae's nurseries live for only a few million. They race through their nuclear fuel in a cosmic sprint, ending their brief lives in a final, spectacular detonation that can, for a few glorious weeks, outshine an entire galaxy of normal stars. The implications of this factory-like output are profound. Each supernova is a cosmic forge, a crucible of immense temperature and pressure where the universe's heavy elements are created. Within the heart of the explosion, atoms are fused together into new, heavier elements like iron, gold, and uranium. Then, the blast itself hurls these newly forged materials far out into space, seeding the surrounding interstellar medium with the raw ingredients for rocky planets and even life itself. This ongoing cycle of death and dispersal is what makes the Antennae so chemically rich and turbulent. The frequent shockwaves from these explosions ripple through the galactic gas clouds, simultaneously compressing some regions to trigger the next wave of star formation while violently shredding others. It is a self-perpetuating cycle of chaos where stellar death directly fuels the conditions for more stellar birth and more subsequent death. The entire system is kept in a state of intense, energetic agitation by this relentless fireworks display. Without this constant bombardment of energy from supernova, the Antennae would be a much calmer and far less interesting place. It is this very turbulence that helps to churn the galactic gas, launch the fountains of molecular material, and shape the ultimate destiny of the merging galaxies. What kind of bizarre stellar remnants are left behind in the wake of this non-stop demolition derby? Scattered throughout the vast volume of the colliding system is a faint, pervasive glow, a ghostly luminescence that outlasts the brilliant clusters and violent explosions. This is the 13th strange phenomenon, the diffuse light of the Antennae, and it is made of stars that have been permanently lost. These are not the runaway stars flung out in dramatic slingshots, but a far more numerous population of common suns, gently but irrevocably stripped from their galactic homes by the slow, persistent tug of gravity. During the chaotic dance of the merger, as the galaxies swung past each other, their gravitational fields plucked countless individual stars from the outer fringes of their disks and halos. Unlike dense gas clouds that feel friction and collapse, these stars were simply gravitationally nudged onto new trajectories that carried them away from the main galactic bodies forever. They now drift in the immense space between the two colliding cores, a vast cloud of isolated suns, each one an island in the dark. This collective glow, known as intracluster light, is incredibly difficult to detect. It is 1,000,000 times fainter than the darkest night sky visible from Earth, requiring immense exposure times and sophisticated processing to tease out from the background blackness of space. Yet its existence is a direct measure of the merger's efficiency at dismantling galaxies. The brightness and extent of this diffuse halo tell astronomers exactly how much stellar material has been truly liberated, providing a forensic tool to weigh the destructive power of the collision. What does this mean for the future of these exiled stars? They are now part of the intergalactic medium, destined to orbit the merged galaxy not as part of a neat disk but as a vast spherical swarm. They will never again be part of a dense, star-filled spiral arm. Any planets orbiting these stars are now on a perpetual journey through the cold, empty voids between galaxies, their night skies devoid of any other bright suns, dominated only by the fading glow of the distant galactic core they once called home. This process is a fundamental part of how giant elliptical galaxies, the expected final product of this merger, form their extended stellar halos. The faint light we see in the antennae is a preview of that future, a glimpse of the lonely stellar haze that will one day envelop the entire system. It forces us to confront a sobering reality of cosmic collisions, that for every brilliant new star born in the chaos, countless others are sentenced to a quiet, eternal exile. This frantic cycle of stellar death is leaving a permanent chemical mark on the entire system. The interstellar gas of the Antennae Galaxies carries a strange and unique fingerprint, a peculiar chemical signature that sets it apart from more tranquil galaxies. When astronomers analyze the light from this gas, they find it is unusually rich in certain heavy elements, the kind forged only in the hearts of massive stars and scattered by their violent supernova deaths. This is not a balanced, well-mixed recipe. It is a lopsided abundance, a direct result of the merger's relentless starburst. Think of a busy industrial city where factories are constantly pouring specific pollutants into the air and water. The antennae are a cosmic version of this, with supernova acting as the factories. The sheer number of these explosions, happening in such a concentrated period of time, is flooding the local environment with a specific cocktail of freshly minted elements like oxygen, neon, and magnesium. These are the ashes of the most common type of massive star explosions. Because the starburst is so recent in cosmic terms, these elements have not had time to diffuse evenly throughout the entire galactic system. They are concentrated in the regions of most intense activity, creating chemical hotspots where the next generation of stars will form from this newly enriched material. This provides a rare, real-time look at a process called galactic chemical evolution. Normally, we see galaxies at a single moment in time, with their element ratios representing the accumulated history of billions of years of star formation. But here, we are catching the system in the act of polluting itself. We can see the enrichment process happening right now, witnessing how a major galactic event can rapidly alter the chemical destiny of an entire system. The next stars born from this gas will be fundamentally different from their predecessors. They will be born with a higher metallicity, a term astronomers use for the abundance of elements heavier than hydrogen and helium. This matters because the amount of metals in a cloud of gas influences how easily it can form planets. A system like the antennae is effectively fast-tracking the production of the raw materials needed for rocky worlds, seeding its future with the potential for terrestrial planets on a scale most galaxies could never achieve. What strange new worlds might eventually coalesce from this chemically rich, yet violently churning cosmic environment? At the heart of this cosmic turmoil, two brilliant cores still stubbornly hold their ground. These are the nuclei of the original galaxies, each one a dense, blazing city of stars orbiting a monstrous secret, a supermassive black hole. For now, they remain distinct, separated by a gulf of thousands of light years, but their dance is a slow, inevitable spiral toward a single, catastrophic embrace. This is the double nucleus puzzle, a ticking clock at the center of the collision. We are witnessing the calm before an event of almost unimaginable violence. The two black holes, each weighing millions of times the mass of our Sun, are gradually losing orbital energy. They do this by gravitationally slingshotting stars that venture too close, flinging them away at tremendous speeds and inching ever closer to one another with each stellar interaction. This process is a cosmic countdown. Once they draw near enough, their fate is sealed. They will begin to orbit each other in a binary pair, a dance of titans that will churn the very fabric of space-time around them. This final merger will not be silent. As the two black holes spiral inward at a significant fraction of the speed of light, they will ripple the cosmos. Their immense acceleration will generate gravitational waves, distortions in space itself that travel outwards at the speed of light, stretching and squeezing everything in their path. Think of the most powerful earthquake ever recorded, but one that propagates not through rock, but through the underlying grid of reality. For a brief, spectacular moment, this single event in the Antennae Galaxies would release more energy than all the stars in the observable universe combined, all channeled into these silent, invisible ripples. While this final merger is still millions of years in the future, its detection would be the ultimate confirmation of a key prediction of Einstein's theory of relativity and a crowning achievement for observatories like LIGO and Virgo. It would also solve a major mystery in astronomy: how supermassive black holes in the centers of galaxies grow to such immense sizes. The antennae are showing us one of the primary methods, the colossal mergers of galaxies and their dark, beating hearts. This future cataclysm is not just an endpoint, it is a transformative event that will dictate the final form of the new galaxy, violently settling the stars into a stable, elliptical shape and ending the era of frantic star birth. The puzzle of the double nucleus is really a question of ultimate destiny, a reminder that even in this scene of brilliant creation, the most profound force remains gravity's relentless, unifying pull. Above the brilliant glow of newborn stars and the radio roar of supernova remnants, an even more energetic mystery may be hiding. The Antennae Galaxies could be a source of high-energy gamma rays, the most powerful form of light in the universe. This potential phenomenon sits at the frontier of our knowledge, a whisper of pure energy that could have two utterly different origins. The first and more conventional explanation points to the galaxy's relentless violence. The shockwaves from all those supernova explosions act like natural particle accelerators, far more powerful than anything we could build on Earth. These shocks can whip protons and electrons to nearly the speed of light, creating a fog of cosmic rays. When these ultra-fast particles collide with the nuclei of atoms in the interstellar gas or with photons of starlight, the impacts can generate gamma rays. It would be a natural consequence of the antennae's status as a supernova factory, but there is another, more exotic possibility. These gamma rays could be a signal from the missing dark matter itself. Some theories suggest that dark matter particles are their own antimatter counterparts. When two such particles collide, they would annihilate each other in a flash of energy, potentially producing gamma rays with a very specific signature. The dense, chaotic environment of the antennae, where dark matter is being violently stirred, could be the perfect place for these rare annihilations to occur. This is why telescopes like the Fermi Gamma Ray Space Telescope have spent years staring at this colliding system. Detecting a clear gamma ray signal would be momentous, but its meaning depends entirely on the energy of those rays. If the gamma rays match the profile expected from cosmic ray collisions, it would confirm our understanding of particle acceleration in extreme environments. But if they carry a unique, sharp energy signature that cannot be explained by any known astrophysical process, it could be our first direct glimpse into the nature of dark matter. The debate continues because the results are so tantalizingly faint and difficult to separate from the background noise of the universe. The antennae are not a blazing beacon in gamma rays, but a faint, ambiguous glimmer. This very ambiguity is what makes the research so active and so critical. The colliding galaxies are presenting us with a cosmic riddle, written in the most powerful language the universe knows, and we are only just learning how to listen. This cosmic collision was never a perfect head-on impact. The resulting wreckage is fundamentally lopsided, a truth revealed in the ghostly halo of neutral hydrogen gas that envelops the entire system. This hydrogen is the primary fuel for star formation, the cold, atomic raw material waiting to be used. Yet its distribution is strikingly uneven, with vast, dense clouds concentrated more heavily around one of the galactic cores while the other appears comparatively starved. This is not a random accident, it is the permanent signature of the collision's glancing blow. When the two galaxies first swept past each other, they did not strike center to center. It was an off-center impact, a gravitational sideswipe that transferred immense momentum from one galaxy to the other. Think of two cars in a terrible, sliding T-bone collision, where one vehicle is sent spinning while the other is knocked forward. The gravitational forces in this cosmic crash acted similarly, effectively dragging a disproportionate amount of the diffuse hydrogen gas from one galaxy and depositing it around the other. This stolen fuel now dictates the future of the entire merger. The galaxy that captured the extra gas is destined to become the dominant partner, its core glowing brighter and its starburst activity likely persisting for longer. The gas-poor core, meanwhile, may see its star formation begin to wane sooner, its stellar population aging without a fresh supply of fuel. This asymmetry ensures that the final, merged galaxy will not be a perfectly smooth ellipse. Its structure will bear the scars of this ancient theft, with one side potentially more populated and brilliant than the other for billions of years to come. The entire system's center of mass is now shifted, and the ongoing dance of the two nuclei is weighted toward the gas-rich side. This lopsided fuel tank is a powerful reminder that the initial conditions of a collision, the angle and the speed, echo across cosmic time, permanently writing the story of the collision into the very shape of the new galaxy it creates. Threading through this entire chaotic scene are invisible lines of force, powerful magnetic fields that have been twisted and amplified by the violence of the merger. We can detect their presence by observing a specific property of the radio waves emanating from the antennae, a phenomenon known as polarization. When radio emissions are polarized, it means their electromagnetic waves are vibrating in a preferred direction, a clear sign they have been organized by the grip of a magnetic field. The patterns we see are not random. They reveal a cosmic tapestry of magnetic lines, tangled into knots and stretched into vast arcs by the churning motions of the collision. These fields are far more than passive spectators. They are active players shaping the destiny of the galactic material. Imagine these magnetic field lines as a network of invisible highways and fences crisscrossing the chaos. They channel the flow of ionized gas, guiding it along specific paths and preventing it from drifting freely in all directions. A cloud of gas that might have collapsed to form a star in one location is instead funneled by these magnetic forces toward a different region, concentrating the raw material for star formation in some areas while starving others. This magnetic guidance system adds another layer of incredible complexity to the starburst process, helping to explain why star clusters form where they do. Yet the relationship is a two-way street. The magnetic fields are themselves being forged and sculpted by the merger's turbulence. Every shock wave from a supernova, every collision between giant gas clouds, and every sheer motion as the two galactic disks grind past each other acts like a cosmic dynamo. These motions stretch, fold, and strengthen the magnetic fields, pumping energy into them until they become powerful enough to, in turn, influence the very gas motions that created them. It is a self-reinforcing cycle, a feedback loop of cosmic power where turbulence builds the magnetic fields, and the magnetic fields then govern the turbulence. This intricate dance determines not just where stars are born, but also how energy is distributed throughout the system, influencing everything from the expansion of supernova bubbles to the launching of those galactic-scale fountains of molecular gas. The amplified magnetism of the antennae offers us a rare glimpse into a fundamental, yet often hidden, aspect of galaxy evolution, proving that the forces at work here are not solely gravitational, but electromagnetic as well. This stellar chaos is also a forge for new worlds, but the planets born here would be unlike any we know. Within those superstar clusters, where 1,000,000 suns are packed into a relatively tiny volume, the night sky would be a perpetual blinding daylight. Any planet forming in such a neighborhood would look up to see not a black expanse dotted with stars, but a brilliant, continuous canopy of stellar neighbors, some so close they would appear as large as our own moon. The very concept of night would be alien. The challenges to survival, however, are immense. The first threat is radiation. In our quiet solar system, the sun's steady light allowed life to emerge over billions of years. But in the core of a superstar cluster, a young planet would be bombarded by intense ultraviolet and X-ray radiation from hundreds of massive, nearby stars. This relentless energy would scour the atmosphere of any fledgling world, stripping away its protective layers and boiling off any liquid water long before life could even dream of beginning. The second, more violent threat is gravitational instability. With so many stars in such a tight space, their gravitational pulls constantly tug at each other. A planet peacefully orbiting its star could be violently wrenched away by a close stellar passage, sent careening into the void as a rogue planet, or have its orbit stretched into a deadly, elongated ellipse that brings it searingly close to its sun before flinging it back into the frozen depths of space. Planetary systems here would be fragile and short-lived, yet for all this danger there is a strange potential. The gas and dust from which these planets would form is chemically rich, seeded with heavy elements from countless supernovae. This could lead to an abundance of rocky, metallic worlds, planets with compositions far stranger and more varied than those in our own galactic backwater. Imagine a planet with a crust made of rare minerals, or one that forms much closer to its star, shielded by some fluke of orbital mechanics. The very planets that do manage to hold on in the outer reaches of a cluster might become time capsules. If the cluster itself eventually disperses, as many do, these hardy survivor worlds would be set adrift through the galaxy, each one a lonely testament to the violent, brilliant cradle where it was born. This final act of the galactic merger is a slow and stately fade to black. The brilliant, chaotic starburst that defines the antennae today cannot last. As the two galactic cores complete their final, deadly spiral and merge into one, the very source of the violence will be extinguished. The immense gravitational forces that have been violently squeezing gas clouds for millions of years will finally relax, settling into the stable, spherical grip of a new, single elliptical galaxy. Without this constant compression, the rampant star formation will cease. The great factory of stars will shut down, its fuel either consumed or expelled. The dazzling arcs of the tidal tails, those iconic streamers of exiled stars, will not snap back. They have achieved escape velocity and will continue their lonely journey, slowly fading and dispersing over billions of years, becoming a faint, extended halo around the new galaxy. The final product will be a red and dead elliptical galaxy, a cosmic retirement home for aging stars. Its distinct spiral arms will be entirely erased, replaced by a smooth, featureless glow of ancient red suns. The vibrant blues of short-lived massive stars will be gone, having long since exploded, leaving behind a population of longer-lived, cooler stars to dominate the light. This new galaxy will be a far quieter but far more massive place than either of its progenitors. All that frantic energy, all that brilliant creation and destruction ultimately leads to this serene and stable conclusion. It is the universe's way of bringing order to chaos, a gravitational peace treaty written in starlight. Yet this quiet end is not an emptiness. It is a legacy, a galaxy enriched with the heavy elements forged in its violent past, now ready to seed future generations of stars and planets in a much more tranquil era. This violent and brilliant collision is not just a spectacle, it is a time machine. The Antennae Galaxies offer a front row seat to a process that was fundamental to building the universe we see today. For astronomers, this system is a priceless laboratory, a nearby template that deciphers the ancient history of galaxy growth. Across the vast depths of space, telescopes capture the faint, blurred light of galaxies in the early universe, many of them colliding. But these distant systems are too far away to see the intricate details, the individual star clusters, the spewing fountains of gas, the hidden black holes. They appear as little more than smudges of light. By studying the antennae in such exquisite, close-up detail, we learn what to look for within those faint, cosmic smudges. When we see a distant galaxy glowing intensely in the infrared, we now understand that we are likely witnessing a similar dust-shrouded starburst. When we detect unusual radio lobes, we can infer the presence of amplified magnetic fields and furious supernova activity. The antennae provides the Rosetta Stone, allowing us to translate the simple light signatures from the deep past into a rich story of gravitational encounters, stellar birth, and chemical enrichment. Every strange phenomenon we observe here, from the superstar clusters to the lopsided gas distribution, becomes a key diagnostic tool. It helps us calibrate our models and refine our simulations of how galaxies evolve over billions of years. We can essentially run the experiment of the antennae's merger in a computer, then compare the results to our real-world observations, checking if our understanding of the underlying physics is correct. This process confirms that major mergers were the primary engines for building the most massive galaxies in the universe, transforming small, disordered systems into the grand ellipticals we see in the modern cosmos. Without this nearby laboratory, the story of our cosmic origins would remain locked in those faint, distant lights, a beautiful but indecipherable code. The antennae gives us the key, revealing that our own Milky Way, for all its current serenity, was likely assembled through similar acts of violent, creative destruction long ago. The iconic portrait of the Antennae Galaxies, captured by the Hubble Space Telescope, is a masterpiece of cosmic violence. We see those brilliant blue star clusters and dark, swirling ribbons of dust set against the soft glow of older stars. It is a beautiful image, but it is also a partial truth, like seeing only the surface of a stormy ocean. Hubble's visible light eyes show us the light that escapes the chaos, but they cannot penetrate the thickest clouds of dust where the most intense action is hidden. Then came the James Webb Space Telescope with its revolutionary infrared vision. Where Hubble saw opaque darkness, Webb sees a universe on fire. It peers straight through the veils of dust as if they were barely there, revealing a hidden landscape of star formation that Hubble could only hint at. The contrast is staggering. The same regions that appeared as dark voids in Hubble's view are now blazing with the light of countless newborn stars, their intense radiation heating the dust that once concealed them, causing it to glow in infrared. Webb has identified specific, massive pockets of stellar birth that were completely invisible before, tucked deep within the overlapping galactic cores. These are not just a few extra stars, they are colossal nurseries, fundamentally changing our sense of the starburst's true scale and intensity. By comparing these two legendary views, we are not just seeing a prettier picture. We are witnessing a fundamental shift in our perception. Hubble showed us the aftermath of the explosion, the shrapnel flying through the air. Webb allows us to look directly into the epicenter of the blast itself, watching the fireworks ignite in real time. This powerful synergy between visible and infrared light gives us a complete, three-dimensional understanding of the collision, proving that the true heart of this cosmic drama was always hidden in plain sight, waiting for the right eyes to see it. While the Hubble and Webb telescopes paint a picture in visible and infrared light, the Chandra X-ray Observatory reveals a completely different layer of reality. It sees the universe in the language of pure energy, mapping a landscape of violence and extreme heat that is entirely invisible to our eyes. Chandra's vision uncovers the searing afterglow of stellar cataclysms and the hidden banquets of cosmic predators. It shows us the antennae not as a collection of stars, but as a cauldron of high-energy phenomena. The most striking features in its view are the brilliant pinpoint flashes of light. Each one is an ultra-luminous X-ray source, a beacon signaling the presence of a black hole or neutron star in the act of feeding. These are not the quiet, dormant remnants of dead stars. They are active, voracious systems where a stellar corpse's immense gravity is tearing gas from a companion star. As this stolen matter spirals inward at nearly the speed of light, it forms a disk so hot that it glows with X-rays, shining with the power of 10,000 suns. Chandra has catalogued dozens of these point sources, creating a map of the most energetic residents within the colliding galaxies. But the space between these brilliant points is not empty. It is filled with a faint, pervasive fog of X-rays, a diffuse glow that blankets the entire system. This is the signature of gas heated to millions of degrees, a superheated plasma that fills the vast expanses between the stars. How does gas become so unimaginably hot? The primary engine is the relentless shock waves from thousands of supernova explosions. Each stellar death sends a powerful blast wave racing through the interstellar medium, compressing and heating the gas to extreme temperatures, like countless underwater explosions constantly churning and boiling an ocean. Furthermore, the fierce stellar winds from all those massive newborn stars collide with each other, and with slower moving gas clouds, creating turbulent regions of intense friction and heat. This hot, diffuse gas is a crucial component of the galactic ecosystem. It represents a massive reservoir of energy that helps to regulate the future of star formation. Its immense pressure can prevent giant molecular clouds from collapsing, effectively putting a brake on the very starburst that created it. At the same time as this hot gas expands and flows outward, it can carry with it the heavy elements forged in supernova, chemically enriching the entire galactic environment. Chandra's X-ray vision completes our picture of the antennae, revealing the incredible thermal and kinetic energy that powers the collision. It shows us that the true violence of this merger is not just in the birth and death of stars, but in the superheated, invisible atmosphere that their lives and deaths have created. If this hot gas tells the story of the energy now flooding the system, what does it mean for the eventual cooling and quieting of this cosmic storm? Beneath the violent glow of X-rays and the brilliant light of new stars lies the cold, dark fuel for this entire cosmic fire. The Atacama Large Millimeter-Submillimeter Array has peeled back these energetic layers to reveal the system's deep, frozen skeleton. Its observations map the distribution of frigid molecular gas, the raw, unlit material from which every star in the antennae must form. What it reveals is not a formless haze, but an architecture of incredible complexity, a web of dark matter woven through the chaos. ALMA sees the universe in long wavelengths, detecting the faint radio whispers emitted by molecules like carbon monoxide as they drift in the cold, dense voids between the stars. This is the phase of gas that exists just before gravity takes over, the calm before the storm of stellar birth. The array's incredible resolution has uncovered a hidden landscape of filaments and knots. Vast river-like structures of this cold gas flow through the colliding galaxies, and at their intersections we see dense, collapsing clouds, the direct precursors to the superstar clusters that dominate the visible light view. These are the cradles caught in the act of tipping over the edge from quiet cloud to brilliant nursery. How does this intricate network form? The titanic forces of the merger are sculpting it. As the two galaxies grind together, their gravitational interplay and the constant shockwaves from supernova compress and stretch the interstellar medium, pulling the gas into these long, thin threads. It is a natural consequence of chaos, like wind carving sand into ripples. Gravity then does the rest, pinching the densest parts of these filaments, causing them to fragment into those individual, collapsing knots that will each ignite into a cluster of stars. This revelation connects the largest scales of the collision to the smallest scales of star formation. We can now trace a direct line from the galactic collision's gravitational shock to the formation of a cold gas filament, to the pinching of a core, and finally, to the brilliant flash of a new stellar cluster. ALMA has provided the missing link in the chain, showing us the blueprint of creation that was always there, hidden in the cold and the dark, waiting for the right instruments to reveal its profound structure. This cosmic laboratory offers more than just a show of force. It provides a critical yardstick for measuring the universe itself. The violent demise of certain stars within the Antennae Galaxies has become a key tool for astronomers grappling with the most fundamental question in cosmology: how fast is the universe expanding? This expansion rate is described by a single number known as the Hubble constant, and pinning down its exact value has proven to be one of the greatest challenges in modern science. The Antennae, with its prolific output of supernova, provides a unique testing ground. Specifically, astronomers search for a special class of exploding star known as a Type Ia supernova. These are not the deaths of single, massive stars, but the catastrophic detonations of white dwarf stars in binary systems. A white dwarf is the dense, Earth-sized core of a star like our Sun after it has died. If it orbits a companion star and siphons off too much material, it can cross a critical mass threshold and undergo a runaway nuclear fusion reaction, exploding with a predictable, standardizable brightness. This predictable peak brightness is what makes them so valuable. Think of it like a standard light bulb. If you know a 100-watt bulb always puts out the same amount of light, you can calculate how far away it is by how dim it appears to you. A Type Ia supernova acts as a cosmic 100-watt bulb. By observing these explosions in the Antennae Galaxies and carefully measuring their apparent brightness from Earth, astronomers can calculate a very precise distance to the system. This measurement is a crucial rung on the cosmic distance ladder, a sequence of methods used to measure ever greater distances across the cosmos. The distance to the antennae, confirmed by these stellar explosions, helps to calibrate other distance measuring techniques. This, in turn, refines our value for the Hubble constant because we can compare the galaxy's recession speed, how fast it is moving away from us due to the universe's expansion, with its accurately known distance. The antennae's chaotic environment, which produces so many of these standard candles, therefore becomes a cornerstone for measuring the scale, age, and ultimate fate of the entire universe. Yet this very process has revealed a puzzling tension, as measurements from different methods yield slightly different expansion rates, a discrepancy that hints at new physics or hidden cosmic ingredients. What other secrets about the universe's fundamental structure might be unlocked by continuing to watch this distant collision? The violent creation we witness in the antennae is not an anomaly, it is a fossilized echo of the universe's youth. This colliding system is a living relic, a nearby template that shows us how most massive galaxies were built in the early cosmos. Billions of years ago, the universe was a much smaller, denser, and more chaotic place. Galaxies were packed closer together, and colossal mergers like this one were not rare spectacles. They were the standard mechanism for growth. The Antennae Galaxies offer us a front-row seat to a process that was once universal, a local window into the deep past. Its intense starburst, producing millions of new stars in a frantic rush, perfectly mirrors the furious star formation rates we detect in the faint, red-shifted smudges of primordial galaxies. Those distant objects are too far away to see in detail, but by studying the antennae, we understand what we are looking at. The rapid assembly of superstar clusters here is a direct replay of how the first great globular clusters formed and came to orbit ancient galaxies. Even the growth of the supermassive black holes at their cores follows this ancient script. In the early universe, black holes grew to immense sizes not by slowly nibbling on gas, but through colossal feasting during major mergers, just as the black holes in the antennae are likely doing right now. This local collision provides the crucial translation key for the distant universe. Every strange phenomenon we catalogue here, from the lopsided gas distribution to the amplified magnetic fields, helps us interpret the faint signals from galaxies whose light has been traveling for over 10 billion years. The antennae are not just a pair of galaxies crashing, they are a time capsule preserving the violent, creative processes that built the cosmic world we live in today. Woven into the brilliant infrared glow of cosmic dust is a subtle but unmistakable signature, a series of specific chemical fingerprints that have long puzzled scientists. These are the unidentified infrared emission bands, a complex spectrum of light that points to something astonishingly organic flourishing within the violence. The specific wavelengths of this light act like a barcode, matching the vibrational energy of certain molecular bonds, and the best match we have is for a class of molecules known as polycyclic aromatic hydrocarbons. That is a complicated name for a relatively simple concept. Picture them as tiny, flat flakes, like microscopic snowflakes or fragments of graphite, made of interconnected rings of carbon and hydrogen atoms. They are essentially the sooty leftovers from incomplete combustion, the kind of stuff you find in car exhaust or a charred piece of toast, but here they exist on a truly cosmic scale. Their presence in the antennae is a profound mystery. How do such complex, carbon-rich molecules form and survive in an environment being constantly scoured by intense radiation from massive stars and shattered by supernova shockwaves? One school of thought suggests they are incredibly resilient, forming right in the thick of the chaos in the dense, shielded cocoons of gas clouds where they are constantly being broken apart and reassembled. Another theory proposes they are fragile refugees, forming in the quieter outskirts of the system and then being blown into the turbulent center by galactic winds, where they briefly light up before being destroyed. This debate is not just academic. These molecules are fundamental building blocks. Under the right conditions, they can clump together, forming even more complex organic compounds, the very precursors to the ingredients of life. Finding them in such a hostile, energetic place as the Antennae Galaxies radically expands our idea of where life's raw materials can arise. It suggests that the violent crucibles of galactic collisions are not just forges for stars and planets, but also for the complex chemistry that might one day lead to biology. The faint, specific glow of these infrared bands is a message from the dawn of chemistry itself, hinting that the path from stellar ash to the first sparks of life may be more robust and more universal than we ever dreamed. In the quiet eons that follow the final merger, the antennae's brilliant chaos will fade into a serene crimson glow. This new elliptical galaxy will be a cosmic retirement home, its once frantic starburst long since exhausted. Its distinct spiral arms will be entirely erased, replaced by a smooth, featureless halo of ancient red stars. The vibrant blue light of short-lived massive stars will be gone, having exploded and left behind a population of longer-lived, cooler suns to dominate the light. This galaxy, now vastly more massive than its progenitors, will drift through its local group in a state of gravitational peace, yet this is not the end of its story. As a member of the NGC 4038 group, it will continue a slow, stately dance with its galactic neighbors. Over billions of years, its immense gravity may subtly influence the motions of smaller, nearby galaxies, perhaps even drawing some into a final, gentle merger that adds the last few stars to its immense halo. This is the natural life cycle of cosmic structures, where violent creation gives way to a long, stable maturity. Looking ahead across trillions of years, this galaxy's fate is tied to the ultimate destiny of the universe itself. In a cosmos dominated by dark energy, it may one day find itself isolated as all other galaxies accelerate beyond its event horizon, leaving it a lonely island of stars in an ever-expanding black void. Its own stars will slowly burn out one by one until the last red dwarf flickers and dies, leaving behind a dark graveyard of stellar remnants. The Antennae's legacy, however, is written into the fabric of the cosmos. The heavy elements forged in its violent past will be incorporated into new generations of stars and planets, perhaps even seeding life in some distant future system. This grand transformation from a chaotic firestorm to a quiet, enduring monument shows us that even the most violent acts of creation are part of a larger, beautiful cycle of cosmic evolution. From superstar clusters to runaway stars and missing dark matter, this journey through 28 cosmic anomalies reveals a universe far stranger than we ever imagined. The Antennae Galaxies are more than just a celestial collision. They are a living library, a cosmic Rosetta Stone that decodes the violent language of galaxy evolution. Every phenomenon we have explored, from the ghostly tidal tales to the faint glow of organic molecules, forms a single, interconnected story. It is a story of how chaos breeds creation, how destruction seeds new worlds, and how the most fundamental forces of nature are laid bare in this colossal laboratory. This single cosmic event teaches us about our own galaxy's past and the eventual fate of all such structures in the cosmos. The next time you gaze up at the night sky, remember that within the seeming stillness lies an endless dance of construction and demolition, happening on a scale that defies human comprehension. We want to know which of these 28 wonders captured your imagination the most. Was it the hidden black holes, the self-regulating gas fountains, or the mysterious absence of dark matter? Share your favorite phenomenon in the comments below and keep looking up with newfound wonder. This cosmic spectacle is not just for the world's most powerful telescopes. You can actually find the faint glow of the Antennae Galaxies from your own backyard, a ghostly echo of the collision hanging in the southern sky. To begin your hunt, you will need to locate the constellation Corvus, the Crow. It is a small but distinctive quadrilateral of stars nestled near the brighter constellation Virgo. On a clear, dark night far from city lights, the Antennae Galaxies lie just south of the star delta Corvus. Do not expect to see the spectacular tidal tails or brilliant star clusters you see in Hubble's images. Through the eyepiece of a moderate-sized telescope, perhaps one with an aperture of at least 8 inches, the antennae will appear as nothing more than a faint, hazy smudge of light. This ethereal patch is the combined glow of billions of stars from the two merging cores, a whisper of the violence happening 60 million light-years away. The challenge of seeing it is part of the magic, a direct connection to the immense scale of the cosmos. For astrophotographers, the antennae presents an ultimate challenge. Capturing its elusive structure requires patience, a tracking mount to compensate for Earth's rotation, and long exposure times. You would take hundreds of individual images over many hours, stacking them together with software to tease out the faint details from the background noise. The final photograph you create will be your own personal map of this cosmic wreckage, a testament to both the power of the event and your own dedication. That faint smudge in your eyepiece is a real place, a living laboratory where galaxies are being remade. Every time you find it, you are not just looking at a picture, you are witnessing an event that will define a new galaxy for eons